my pleasure to introduce Ben Weinkove from Northwestern University. He's going to talk about the Chern-Ricci flow. I'm very happy to see that already so many people are joining this event, and I hope it will go on for the next weeks like this. So thank you so much for your participation. And first of all, thank you, Ben, for accepting to give a talk at our web seminar.
Okay, well, thanks very much. It's a pleasure to be able to give this talk. I would say it's great to see familiar faces, but I don't see that many faces, but at least I'm seeing some familiar names. So I'm going to talk about the Chern-Ricci flow, and I want to give a kind of overview of this topic and indicate what we know so far and what are some open problems. Okay, please let me know if something goes wrong, if you cannot hear me or you cannot see the slides moving. Once I had some problem with that. Okay, so let me begin with some motivation. So M is for us going to be a compact complex manifold, and we're going to have on that manifold a Hermitian metric, and locally in complex coordinates, we'll write that metric as G0 ij bar. Those are the components of the metric in complex coordinates. And so a motivating question is what is a natural evolution equation for which gives a smooth family of Hermitian metrics starting with that initial metric. Oops. So let me begin with the case where G0 is Kähler, and that means that if you take the 1-1 form associated to G0, namely you take your G0 ij bar and then some dzi wedge dzj bar, then that's a closed 1-1 form. Then the Ricci curvature of that metric, so that is the Ricci curvature of the associated Levi-Civita connection, has a very simple formula. It's given by di dj bar of log of determinant of G0. And then the Ricci flow, or in this case, it's usually called the Kähler Ricci flow, since we're dealing with a family of Kähler metrics. So the Ricci flow starting at G0 is a family of smooth Kähler metrics which satisfy the PDE that the time derivative of G is given by minus the Ricci curvature. And then you're starting at this metric G0. So what happens if you start with a metric which is not Kähler? So if you start with the metric G0, which is only Hermitian, not in general Kähler, then there's a problem with the Ricci flow. And that is that if you take the Ricci curvature of the Levi-Civita connection, it's not going to be in general of type 1-1. And so if you look at the Ricci flow starting with that Hermitian metric, it's not going to give you a flow of Hermitian metrics in general. You will lose the property of being Hermitian immediately. And so the Ricci flow does not seem to be the natural flow to look at in this context if we want to look for a flow of Hermitian metrics preserving this complex structure. So that suggests that we perhaps should change the connection. And so what we do is we look at, instead of the Levi-Civita connection, we look at the Chern connection. And this is a connection which satisfies that the G and J are covariantly constant, but the bad part is that we have torsion. So the Chern connection is that particular connection so that the 1-1 part of the torsion vanishes. I can write down the Christoffel symbols. You can see here the formula. Let me not go into the details of this. I'm not going to be using these formulas. So you can write down the Christoffel symbols in terms of the metric. We have the torsion, which is the difference of the Christoffel symbols, where we interchange the lower indices. And you can see that in the Kähler case, the Christoffel symbols are symmetric in the lower two indices, and so the torsion vanishes. The curvature is given by a derivative of the Christoffel symbols. And then, so that gives you the full curvature. But we're interested in a kind of Ricci curvature. And a Ricci curvature is a trace of the curvature. So in this Hermitian case, you can take different kinds of traces. So one thing we can do is we can take the trace with respect to the second two indices, and that's called the first Chern-Ricci. Or you can take the trace with respect to the other two indices, and that's the second Chern-Ricci. There are other traces you can take, but those don't seem to be very natural. But these are two quite natural traces you can take. And they're called the first Chern-Ricci and the second Chern-Ricci. I'm going to be focusing on the first one, and rather than call it the first Chern-Ricci, I'm just going to call it the Chern-Ricci. And this one has a nice property that that it has the same formula as in the Kähler case in terms of the log of determinant. So it's given by Rij bar is minus di dj bar of log of determinant of G. Okay. Oops. Sorry. So, so what is the Chern-Ricci flow? The Chern-Ricci flow is where we evolve these Hermitian metrics by the negative of the Chern-Ricci curvature. And so it has the same form as the Kähler-Ricci flow. And indeed, in this case, as I said, the Rij bar is simply minus di dj bar log of determinant of G. So in that sense, it's exactly the same formula. Where does it differ? It differs because it's not the Ricci curvature of the Levi-Civita connection. So it really is not the Ricci flow. We're flowing with respect to the Ricci curvature with respect to this Chern connection, this particular connection, but then this particular trace of the curvature. So of course, when G naught is Kähler, this exactly coincides with the Ricci flow. Now, this is not the only flow which generalizes the Kähler Ricci flow to this Hermitian case. You could take the other Chern-Ricci, the second Chern-Ricci, and indeed many people have done that. And so this was considered earlier by Streets and Tian. They considered a whole family of flows of this type, where you take ddt of Gij as minus the second Ricci, and they added an extra term. So I'm calling it Q. And I'm not going to be specific about what it is. There are various different choices you can make in that term Q, and they have different properties. So for example, Streets and Tian discovered that a particular choice of this Q gives you a flow which preserves the property of being dd bar closed. We'll say a bit more about that later. That's also preserved for the Chern-Ricci flow. A different choice was introduced by Ustinovsky, and for another choice of Q, he showed that the positivity of the curvature in the Griffith sense is preserved along that flows. And then Ustinovsky's flow, I think, also comes up as a special case of the anomaly flow due to Fong, Pickard, and Zhang, and this was just properties of this being proved by Fong and Fei. And then Manchun Li rather recently considered the flow where Q is equal to 0, and that has some nice properties too. So I'm not going to talk about these other kinds of flows which are based on the second Ricci curvature, but I think that it does suggest that in the Hermitian case, there is maybe not one single flow which has all the right properties you want. Maybe we need to consider several different equations. The Chern-Ricci flow has some rather nice properties though, and I want to describe those properties. And it turns out we know an awful lot about it, especially in the case of complex surfaces, like complex dimension 2. And that's what I want to focus my talk on. Okay, so let me mention two important properties of the Chern-Ricci flow. One of them is that if you start with a metric which is Kähler in some set, then as you flow, it remains Kähler in that set. And the reason is that you're flowing by something which is closed. The Chern-Ricci form is locally dd bar exact, and therefore it doesn't change the property of being closed. So where you start being Kähler, you will remain being Kähler. So that's a nice property of it. The other important property, and this is what we use to prove all the results that I'm going to talk about today, is the fact that the Chern-Ricci flow, because it has this nice formulation in terms of the log of the determinant, can be written as a parabolic complex Monge-Ampère equation in terms of a potential function. So you can reduce this equation of tensors into an equation of functions, scalar functions. So here phi is just a real valued function on my manifold. Let me be more explicit, but I'm not actually going to use this formula, but just to give it to you right now. So if phi is this, again, this real valued function phi, if it solves this parabolic Monge-Ampère equation, d phi dt is a log of determinant of g hat ij bar plus di dj bar phi over determinant of g naught. And this g hat is a set of reference, they're not exactly metrics, they're reference forms, given by g naught ij bar minus t r ij bar g naught. So if you, given phi solving this parabolic complex Monge-Ampère equation, then if you set g of t to be g hat ij bar plus di dj bar phi, then that will solve this Chern-Ricci flow, which is d dt of g is minus the Ricci. So let me remind you, so what is the complex Monge-Ampère equation? The complex Monge-Ampère equation says that you take the complex Hessian, di dj bar phi, of a real valued function, and you take its determinant. And so that's the complex Monge-Ampère operator. If you work in a compact manifold, you have to add, you also insist that dd bar phi is bigger than 0. So that you can never have such, you can never have non-trivial such functions on a compact manifold. So on a compact manifold, you have to add some metric usually. And so that's what you're doing here. You're adding this metric g hat and you're taking the determinant. So that's the complex Monge-Ampère operator. It turns out to be, you have to take the log here, and then you put the d phi dt on the left-hand side. So that's the parabolic complex Monge-Ampère operator. So yeah, just to mention that this g hat, technically speaking, is not a metric, but at least it's a metric for small values of t. And in many cases, you can make some small changes to the equation to replace it with a metric. Okay. So let me mention, I'm not going to go in depth on this, but let me mention a fairly recent application of the Chern-Ricci flow, where it was used to actually prove a result about the Kähler-Ricci flow, and in turn was used to prove a classification result. So this is a result of Lee and Tam from a couple of years ago. And what they did is they actually looked at the case of non-compact, complete manifolds under the assumption of positive bisectional curvature. And the reason they're interested in this is there's a well-known conjecture of Yau, which is that all such manifolds should be biholomorphic to Cn. In fact, they consider the case of non-negatives. They don't need strictly positive. And they make this extra assumption, which is that you have maximum volume growth, but I'm not going to go into the details. So how does the Chern-Ricci flow come in? So the idea is that if you're given such a manifold, if you can produce a solution of the Kähler-Ricci flow, it turns out that you can actually prove that under suitable assumptions that it's biholomorphic to Cn. And so that was a result of Chow and Tam. So what they wanted to do is construct sorry, I should be more specific. They want to construct a solution of the Kähler-Ricci flow with bounded curvature on this manifold. And they do it by using the Chern-Ricci flow. And let me just draw a picture here. So the idea is that if you're given a Kähler manifold on your manifold, a Kähler metric on your manifold, here I'm supposed to be drawing a kind of non-compact complete manifold here going up to infinity. The difficulty they have is that they don't have any control on G naught at infinity. So the curvature may be unbounded. So what do? Well, they kind of, they take some large set on the manifold. And what they do is they modify G naught to make it into a complete metric, G tilde naught, on some bounded set, which is some large bounded set. And what they do is they modify it conformally. And you can see now why the Hermitian, why you have to leave the category of Kähler metrics. Once you take a Kähler metric and you start modifying it conformally, you're going to lose the Kähler condition. You're going to lose, it's not going to satisfy this differential equation that d of omega is 0. But on the other hand, you will remain a Hermitian metric. You can always take any Hermitian metric and multiply it by e to the f, where f is some smooth function, it will remain a Hermitian metric. So they modify it, and they get a Hermitian metric with bounded curvature on some bounded set, which is complete. So that and then what they do is they prove that you can get a solution of the Chern-Ricci flow, starting at G tilde naught on this smaller set. But then for a large part of your manifold, it agrees with G naught. And because of this nice property that the solution of the Chern-Ricci, where it starts being Kähler, it remains being Kähler, you get actually a solution of the Kähler-Ricci flow on a large part of your manifold. So they do this for one bounded set, and then you take a sequence of exhausting sets, exhausting your whole manifold, and you get a sequence of Kähler-Ricci flows. And then one has to prove that you can take a limit and obtain a solution of the Kähler-Ricci flow on the whole manifold. Of course, the devil is in the details. You have to get estimates to prove that you can do this in some uniform way. And by doing that, they gave an alternative proof of a result of Gang-Liu, which was proved almost at the same time, which showed that if you have maximal volume growth and non-negative bisectional curvature, then you have to be biholomorphic to see it. So let me go back to the case of now compact manifolds, and the basic question whenever you have any kind of parabolic PDE is you want to ask, well, do we have a solution, and how long does that solution last? So we're interested in when there are solutions to the Chern-Ricci flow, and for how long does that solution exist. So let me begin with a little bit of notation again. So, it's convenient sometimes to go back and forth between talking about metrics and talking about forms. So when we're given a metric, a Hermitian metric G, you can talk about the 1-1 form associated to it. Let's call that omega. It's a positive 1-1 form. It's not closed in general, so it doesn't define any kind of cohomology class, but it's a positive 1-1 form. You can define the Chern-Ricci form. So this is the 1-1 form associated to the Chern-Ricci curvature. Remember, this Rij bar is this Chern-Ricci curvature is given by minus dd bar log of determinant of G, and that's a closed form. It's a declosed form. And so you can write the Chern-Ricci flow in terms of forms instead of in terms of metrics, and it looks like det of omega is minus Ricci of omega. So here's the result about the when the flow exists and for how long it exists. So this is a joint work with Valentino Tassati quite a while ago. So we showed that there exists a maximal, let me say what maximal means in a second, smooth solution omega t to the Chern-Ricci flow for t between 0 and capital T, where capital T is the supremum of all little t positive, such that there exists a smooth function psi on your manifold M as a smooth real valued function psi, such that omega naught minus t Ricci of omega naught plus dd bar psi is strictly positive. So this capital T depends only on omega naught. It's also not difficult to check that if you change omega naught by adding dd bar of a function, that would also not change the capital T, so it's invariant under that. Well, this looks a little bit like a cohomological type condition, and indeed in the case where your manifold is Kähler and omega naught is a Kähler metric, then this result is known for the Kähler-Ricci flow. So initial results in this direction are due to Huaidong Cao and Suji, but this precise statement is due to Tian and Zhang. So in the case of the Kähler-Ricci flow, it corresponds to a cohomological condition. And that says that the flow, the Kähler-Ricci flow, starting at omega naught, will exist as long as the cohomology class omega naught minus t times Ricci of omega naught is strictly positive. That is, has a representative which is positive definite. So here I'm talking about the cohomology, the Dobol cohomology H11. So you take the closed d-bar closed 1-1 forms, quotient out by the d-bar exact 1-1 forms. And just to remind you that the cohomology class of the Ricci curvature is the first Chern class up to some constant multiple. So in the case of the Kähler-Ricci flow, it has this very nice cohomological condition. It's very easy usually to compute what the capital T is. It just depends on your Kähler code and your initial Kähler metric. The point is that in the case of the Chern-Ricci flow, you're starting with a general Hermitian metric. You can't talk about the cohomology class of that Hermitian metric. It's not a closed form, so it doesn't make sense. But still, the analogous result holds, and it exactly corresponds to this capital T. But you know, the question would be, well, can you compute the capital T? And it turns out you can. In many cases, you can. So let me start with two simple cases where you can compute the capital T, and it's actually infinity. And then later, I want to specialize to the case of talking about complex surfaces, that is, complex dimension 2. And in that case, under mild assumption, you can compute the capital T in basically all cases. Okay, so yes, in many cases. So let me mention two special cases. So this is again just recalling what does maximal mean? I guess I didn't say what do I mean by maximal. I just mean that there's the maximal time for which there exists a smooth solution. So that's all I mean. So I know that just from the short time existence result for parabolic equations, there is always a maximal time. You know, it will always exist. There's always going to be some capital. It will always exist for some short times. There will be some maximal time. So just by short time existence and uniqueness. And now we want to figure out what it is. So one special case is, so if there is a metric omega with Ricci of omega, remember this is the Chern-Ricci of omega is equal to 0, omega is just a Hermitian metric, then it's not difficult to see that this capital T is infinity. And this is equivalent to saying on a Hermitian manifold that the first Bott-Chern class is 0. So when you talk about Bott-Chern class, you have to quotient out by d bar exact instead of quotienting out by d bar exact. So in this case, Matt Gill showed that T is infinity. So this is before my work with Valentino. And he showed that omega T converges smoothly to a Hermitian metric omega infinity, which has the Chern-Ricci form of omega infinity is 0. Another special case is if there exists a metric omega with negative Chern-Ricci. Now, in the case, if you have a metric with negative Chern-Ricci, that's rather special. So again, you can see pretty quickly from this definition of capital T that the capital T will be infinity. So this is rather special because such manifolds admit a Kähler metric, because the Chern-Ricci form, if you take minus the Chern-Ricci form, it's positive. But we also said that the Chern-Ricci form is closed, and therefore it's minus the Chern-Ricci form is a Kähler metric. So such manifolds are Kähler automatically. And more than that, you know that they, by work of Yau or Ban, they admit Kähler-Einstein metrics. So in fact, M admits a Kähler-Einstein metric. Valentino and I showed that if you take omega T and you have to rescale in this case, because if you don't, then the volume goes to infinity. So you rescale so that the volume is bounded. And then you can show that if you start with any metric, any Hermitian metric, then it will converge towards the Kähler-Einstein metric. So this Chern-Ricci flow starting at any Hermitian metric on this Kähler manifold will find the Kähler-Einstein metric. So it will converge smoothly to the Kähler-Einstein metric. In the case where your initial metric is Kähler, this is a result due to Weidand-Sau. So then that's the Kähler-Ricci flow. Okay, so what I want to focus my talk on is the case of complex dimension 2. But before I do that, let me begin with complex dimension 1, just as a kind of warm up. Now, in this case, every Hermitian metric is Kähler. That's because remember that the Kähler condition is that the d of omega is 0, but omega is a 2 form. So on a manifold of real dimension 2, you take d of omega, it'll be a 3 form. The 3 form has to be 0. So d omega 0 automatically is satisfied on a Riemann surface. So in complex dimension 1, there are 3 possible behaviors depending on the genus of your surface, the topological genus. So first of all, if M is P1, CP1, the Riemann sphere, then the the capital T is finite. Remember, all of this is now just the Ricci flow because everything is Kähler here. So capital T is finite, and your manifold shrinks to a point as T goes to capital T. Remember that the flow is ddt of the metric is minus the Ricci. In this case, the P1 has a metric of positive curvature, and so you expect your metrics to be shrinking. So you expect the shrinking to occur. So the manifold shrinks to a point as T goes to capital T. If you were to rescale so that your volume is constant, then what you would see is that your metrics would be converging to the round metric, a round metric, a metric of constant curvature on P1. Now, if M has genus 1, so it's topologically a torus, elliptic curve, then the capital T is equal to infinity. And in this case, your manifold admits a flat metric, and the omega T along the Kähler Ricci flow will converge to a flat metric as T goes to infinity. And then if M has genus strictly bigger than 1, then again T is equal to infinity. You have hyperbolic metrics. So you have metrics of constant negative curvature. And in this case, again, so remember that ddt of G is minus the Ricci. So now if your Ricci is negative, like these hyperbolic metrics, you are expecting, oh, I guess I got a question. Is the rate of convergence in the flat case exponential? Yes, in that case, it is known that the conversion is exponential. Yes, that was, well, yeah, again, that's I'm pretty sure is contained already in the work of Hamilton from the early 90s. In the third case, yeah, so these hyperbolic metrics, of course, have negative Ricci curvature. You expect your metric to be expanding because you do ddt of G is minus Ricci. And so you have to rescale. You divide by T, and then the volume will remain bounded, and it converges to hyperbolic metrics. So these results are all relatively all due to Hamilton and Ben Chow. Okay, so let me turn now to the case of complex surfaces. And this is complex dimension 2. And I want to make the assumption that M is minimal. So this means, that, first of all, I'll talk about the case of non-minimal later. So this means that there are no smooth rational curves of self-intersection -1. And this is a natural assumption to make because if you, I guess I have another question, what is the role of genus? The rate of convergence, yeah, that I guess I'm not sure about that. I know it's exponential, but I don't know much more about the, I guess I asked a question about the rate of exponential convergence. That I'm not sure I could tell you that that's yet known to be optimal. So if we, right, okay, minimal surfaces. So if you're given any complex surface which has smooth rational curves of self-intersection -1, there's a process of blowing them down. I'll talk a little bit about that later. And so given any complex surface, you can always, after at a finite number of blowdowns, you can assume that it is minimal. So it's natural to assume that you're working with minimal surfaces just to begin with. And we make another assumption. And that other assumption is we assume that dd bar of omega naught is 0. And this is the condition of Gödel-Schonn. It's not a very strong assumption to make in the sense that if you start with any Hermitian metric, you can always satisfy that condition by simply applying a conformal rescaling. So you can just replace omega naught by e to the f omega naught for some smooth function phi for f, and then you can satisfy that condition. So it's natural to make that assumption, and that condition is preserved along the Chern-Ricci flow because the Chern-Ricci flow you're moving by closed forms, and therefore, and in particular, the dd bar closed. So that condition is preserved along the Chern-Ricci flow. So let me talk about the minimal complex surfaces, and there's many surfaces to talk about, and it's natural to look at what the classification is. Now, the first thing we do is look at Kähler dimension, and that here's the definition. I'm not going to use the definition, but what it does is it's measuring how positive your canonical bundle is. So the Kähler dimension is a number that can either be 2, 1, 0, or negative infinity. And it's defined in the following way. If you look at the space of, vector space of holomorphic sections of your canonical bundle, Km, to some power L is a very large number, and you let L go to infinity, then that behaves like a polynomial. And if it's of order 2, then you say Kähler dimension is 2. That means you have lots of holomorphic sections. If it's 1, then you have Kähler dimension 1. If it's positive and bounded, then you say it has Kähler dimension 0. So that means you have some holomorphic sections, but they don't grow as it goes to infinity. And in the case of negative infinity is when you have no holomorphic sections at all. And then we call that negative infinity. So let me begin with the case of Kähler dimension 2, and let's take omega t to be a solution of the Chern-Ricci flow, which is starting at a Gödel-Schott metric. And I drew a picture here. So this is supposed to be a product of two surfaces of high genus. That would be an example of a minimal surface of Kähler dimension 2. So if at all of these surfaces are projective algebraic, you have lots of holomorphic sections you can embed in projective space. In particular, that means actually you have Kähler metrics. So in this case, we already know you have Kähler metrics, so it's perhaps more natural to look at the Kähler Ricci flow. But you can still ask the question, what happens if you start with a Hermitian metric? What will it do? So it turns out that all of these manifolds admit Kähler-Einstein metrics, but for some of them, the Kähler-Einstein metric will be singular. It will be singular along a subvariety, in fact, or -2 curves. And it's known, so in the case of when you start with a Kähler metric, this is due to work of Suji and Chen Zhang. But in the case of the Chern-Ricci flow, so again, if you have, in the case where you have C1 is negative, that's the result I mentioned before, that's the result with Valentino. In this more general case, it's due to McGill. You get after rescaling, you get conversions to a singular Kähler-Einstein metric, and that convergence is smooth on compact subsets away from the singular set. So then you get relatively nice behavior. Then we go to Kähler dimension 1, and this is the first case where you're seeing, so now we're actually seeing some surfaces which are not Kähler. That is, they don't admit any Kähler metric. And that's what we're more interested in. So let's assume that M admits no Kähler metric. Then it's known from the Kähler classification that M is an elliptic bundle, holomorphic bundle over a Riemann surface. So I'm drawing a picture here which is supposed to describe this. So you have like a Riemann surface as the base, and I'm drawing the fiber as being an elliptic curve or a torus. So it's either this elliptic bundle or you have a finite cover by 1. So what do we expect of this flow? Well, if you think about the Kähler Ricci flow individually on the two factors, if you just took a product, what would you get? Well, you would expect the base to be the volume to be blowing up, to be going to infinity, whereas you'd expect the fiber, the volume to be staying the same because it has a flat metric. So it makes sense to normalize so that your volume is bounded. So you divide by t, but that's going to have the effect of making the fiber shrink to 0. And that's exactly what you see. So you see that if you take omega t divide by t, so that the volume is bounded, and bounded away from 0, then what happens is it converges to, sorry, the volume is bounded, right? What will happen is that the metrics after rescaling will converge to a Kähler-Einstein metric on the base. So you actually want to pull back to the manifold here. And so this is a result of with joint work with Valentino Tassati and Xiaohui Yang. We showed that you get this convergence, and you get C0 convergence as metrics. In fact, we show it's exponentially fast. And if you look at the metrics in the fiber direction, so remember that these fibers, these torus fibers are shrinking. If you rescale so that they have constant volume, they actually converge to the flat metric in the fiber. In the case where you're looking at Kähler dimension 1, where you have Kähler metrics, the situation is actually much more complicated. There are more such manifolds, and you get these singular holomorphic vibrations. And in the Kähler case, that's been, many people have worked on that, starting with the work of Song and Tian. You get some more complicated behavior. So it's actually simpler in the non-Kähler case. And then there's the case of Cadao dimension 0, and I'm drawing a picture, so that would be an example. You could just take a product of toy, that would be an example, a not very interesting one. But in this case, all of these manifolds have the first part Chern class 0, which means that you admit a Chern-Ricci flat metric. And then in this case, it falls into the result I mentioned before by Matt Gill, that the Chern-Ricci flow exists for all time, and you get smooth convergence to a Chern-Ricci flat metric. Okay, so now we move on to the last case, which is Cadao dimension negative infinity. And here there are two cases to consider. One is so some of these manifolds do admit Kähler metrics and some don't. So in the case where M admits a Kähler metric, so here I drew a picture here, it's supposed to be a ruled surface. So you have like a Riemann surface and you have a fiber, which is a P1. So another example would just simply be P2. So in this case, since you have a Kähler metric, it's perhaps less interesting from the point of view of the Chern-Ricci flow. But you can still look at it, take a metric which is not Kähler, what happens? It's not known, but we do know that capital T is finite and the volume goes to 0 in finite time. But apart from this, very little is known. And it's probably very difficult, even in the case of P2. In fact, even the case of the Kähler Ricci flow on P2 is a very difficult problem. I don't know how to prove convergence of the Kähler Ricci flow on P2 without using Parabolic estimates, for example. So it's a difficult problem, even the Kähler Ricci flow. The Chern-Ricci flow probably should be more difficult. So perhaps we're more interested in the case where M does not admit a Kähler metric. And these are known as the minimal class 7 surfaces. So that's from Cadáver's original classification. So if your second Betti number is 0, then these are classified, and they're all either what is known as Hopf surfaces or Inoue surfaces. So let me say a little bit about each of these two types. Okay, the Hopf surfaces. So let me take just the simplest example of a Hopf surface. And this is you take C2 minus the origin, and you quotient out by the equivalence relation, where you just take Z maps to 2 times Z. And here my picture, my rather simplistic picture, is supposed to be 2 concentric spheres in C2. So think of these circles as being S3s of radius 1 and radius 2 inside C2. And the Hopf surface is the area in between, it's like the annulus, it's the area in between these 2 concentric spheres. And what you're doing is you're identifying the inner sphere with the outer sphere. And that's the Hopf surface. And you can see from that picture that it's diffeomorphic to S3 cross S1, because you have this identification of the inner one with the outer one. You're getting this, that's where the S1 is coming from. You see in particular, these certainly don't admit Kähler metrics, because S3 cross S1 has second Betti number 0. I guess I just mentioned that. So in this case, not very much is known, but we at least have a conjectural picture of what should happen. So we do know that, that the Chern-Ricci flow blows up in finite time, and the volume goes to 0. What you can do is you can start with the standard metric. There's a standard metric on the Hopf surface. I'm calling it omega naught here. And you just take dzi Irish dzi bar, divide by z squared. Z squared, I mean absolute value of z1 squared plus absolute value of z2 squared. And you can see that's invariant under this action. Z goes to 2 times z. And if you just start with that metric, you can just write down explicitly what the Chern-Ricci flow is. And you get that as t goes to a finite number, in this case it's 1/2, omega t converges smoothly to a 1-1 form alpha, given by the following formula. It's a non-negative 1-1 form. So let me say a little bit more about that. So this 1-1 form has some, as I said, it's not positive. It has some degenerate directions, and those degenerate directions are in the S3 direction, the tangent to S3. And in fact, if they define a distribution in this tangent space to S3, and if you take the iterated Lie brackets, you generate the whole tangent space to S3. And that implies that, in fact, your manifolds are converging as metric spaces. So in other words, in the Gromov-Hausdorff sense, so they're converging as metric spaces to S1. So you get this convergence. So you're getting this, the S3 factor, at least in terms of metric spaces, is just collapsing, and you end up with this S1. So it's kind of interesting that you end up with something odd dimensional. You start off with this complex surface, and you end up with an S1 along the Chern-Ricci flow. In this particular model case, one might conjecture, and we do conjecture, that you get similar behavior starting at any Hermitian metric, but that's not known. Right. Then the case of the Inoue surfaces. So these are quotients of C cross H. H is the upper half plane. I'm not going to go into the details of the construction. There's actually 3 different types of Inoue surfaces. They have rather complicated construction. They fiber over S1. The fibers are compact 3 manifolds. In all of the cases, the Chern-Ricci flow exists for all time. The behavior turns out to be more analogous to what you get with these elliptic bundles, where you get collapsing of the fiber. So indeed, that's exactly what happens. So in the joint work with Fang and Valentino Tossati and Tao Zheng, we showed that if you rescale your metrics, you get convergence to a 1-1 form omega infinity. And that is, so here you take the hyperbolic metric on H, the Poincare metric, and that descends to a metric on your manifold M. And you get convergence, we get uniform convergence. And if you look at in the sense of metric spaces, you get convergence to S1. So again, you get this collapsing to something odd dimensional. Okay, I should mention the technical condition we make. We have to make some initial conformal change to the metric. So we can't prove that for all initial metrics or even all Gödel metrics. So we have to make some assumption. We believe that assumption can be removed, and I think that Valentino is working on that with Angela, and they believe that you can remove that condition. So that's a technical condition we assume. But so that given that, then we understand what goes on in the case of the Inoue surfaces. So that's good news. On the other hand, the bad news. So if you take now second Betti numbers is positive, we know almost nothing. So in this case, we know that capital T is finite, and we know the volume goes to 0. So that we can prove, but otherwise we know very little about what happens. So in this case, we're now very much in the realm of speculation. These surfaces are not classified. It's a famous problem, probably the most well-known problem in complex surfaces, is to classify the class 7 surfaces. They are classified by Telemann in the case B2 equals 1, but the B2 bigger than 1 is not known. So what's an optimistic conjecture? Well, you might hope that you get some kind of behavior like we saw in the case of the Hopf surface. So some convergence to an alpha, smooth non-negative 1-1 form. Maybe let's be even more optimistic. Maybe that defines some kind of tangent distribution, and it gives you an integrable three-dimensional distribution. And then a leaf of that will give you a sphere in a global spherical shell. So this is all sort of wildly speculative. Why is that interesting? Well, it's conjectured that these global spherical shells exist. If they do exist, it would complete the classification of the class 7 surfaces. What is a global spherical shell? Well, it just means a smooth 3-sphere in your surface with connected complement, and such that it has a neighborhood biholomorphic to a neighborhood of S3 in C2. So of course, every complex manifold admits a smooth 3-sphere with a neighborhood biholomorphic to a neighborhood of the standard 3-sphere. The point is that the complement is connected. Right? So you can always find a small ball in your manifold. The point is that the complement has to be connected. And if you go back to your picture of the Hopf surface, take a sphere in that annulus, and then when you take its complement, the point is because of the identification of the inner and outer spheres, the complement is connected. So that's an example. And indeed, so that's what we expect to see in the case of the Hopf surface. You might sort of optimistically conjecture that holds for the Chern-Ricci flow. I'm not suggesting that this is really going to give a method to solve this global spherical shell conjecture, but one can speculate. Okay, let me, in the last couple of minutes, just say something about what happens if your surface is not minimal. So in all of the above, I was assuming that M doesn't have any of these -1 curves. So let's suppose that you do. And let me make the assumption that the Kähler dimension is not equal to minus infinity, because if it does, it complicates matters a little bit. You can still say something, but it's a bit more complicated. So just ruling out that case. Suppose you have just one minus one curve, then there always exists a map, this holomorphic blowdown map, that takes your minus one curve and blows it down to P. Usually you think of it going in the other direction. So you start with the point P, and you replace the point P with all of the directions through P. Each of those directions is a C in C2, and the lines in C2 are exactly what we mean by so lines through the origin C2 are exactly what we mean by P1. So replace that point by P1. So what do we know in this case? Well, we know if you start with a Hermitian metric on your M, which has this minus one curve, what we know is that the volume of the minus one curve has to shrink to zero in finite time. And so the capital T is finite. And what we showed, again, joint work with Valentino, is that the omega T's are going to converge to some smooth metric outside of E, smoothly on compact subsets. So that's all we know in the general case. If we make this additional assumption, it's a little bit of a cheating kind of assumption. We assume that if you take D of omega naught is on your original M, it comes back, it's the pullback of a smooth form from N. If you assume that, then you can prove more. You can actually prove that you get Gromov-Hausdorff convergence as metric spaces to N comma DT. So I'm not going to go into details here. DT is a metric in the sense of metric spaces on N, which is just defined in terms of this omega T. Mm. And so what happens is that the E actually shrinks to a point, the diameter of E will tend to zero. And you get this Gromov-Hausdorff convergence. And also you can continue the flow on N. And this is so partly due to Valentino, myself, and then Charles-Nier and Tau independently proved that you can continue the flow on N. In the Kähler case, this similar behavior has been seen. So this was, I worked on this with Jan Song. We have some results, some stronger results in the Kähler case. So in the non-Kähler case, we have to make this assumption, which is not very good. This assumption is really saying that you don't have torsion along E. Now, all the difficulty is coming from torsion, so we're kind of removing the difficulty there. So it's not an ideal assumption to make. Other than that, you can come up with examples where this is satisfied. It's not difficult to come up with examples. So you do see this behavior. But of course, an interesting problem would be to remove that assumption. Or maybe, if you remove that assumption, it's false. Maybe it's not true that you get this contracting behavior. So let me, finally, in the last slide, let me mention some open problems. So as I said, what happens if you remove that assumption? Take general initial metrics. What happens? Do we get this finite time contracting? Maybe, maybe not. I think it's an open problem. It could be interesting is to look at this finite time collapsing on Kähler surfaces. This just hasn't been explored at all. So just to mention an open problem there. It's a difficult problem for the Kähler Ricci flow. It could be much more difficult for the Chern-Ricci flow. I think more interesting is to look at the case of Hopf surfaces. There were some partial results, most recently by Greg Edwards, where you can prove some estimates on Hopf surfaces, but we still don't know that we don't have any good convergence result. It's always difficult when you have these finite time collapsing situations. And another interesting approach, as I mentioned, there are many flows you can look at on complex surfaces and complex manifolds. It may be that one has to look at it, has to change the equation. Some novel approach has been suggested by Lenard and Tian, and they suggested in the Kähler case that instead of looking at the Kähler Ricci flow, you look at a kind of elliptic version, elliptic equation, and that is omega is omega naught minus S Ricci of omega. And it turns out to have many of the same kind of properties as the Kähler Ricci flow, but it has the property that you always get a lower bound on the Ricci curvature, so you get some advantage. In the Hermitian case with Morgan Sherman, we have some results, but it's rather preliminary. So that's another interesting avenue to explore. Another avenue is remove the condition that the complex structure is integrable. So you can also look at almost complex manifolds. And there is a flow that one can write down. In the joint work with Chern-Ricci and Valentino, we wrote down a flow. And the latest result in that is due to Tao Zheng, and he does prove you can get a maximal existence time result. Here you take this DD bar log, but now you have to take the 1-1 part, because in general, DD bar, when you're dealing with almost complex manifolds, is not of type 1-1 in general. So that's another avenue to explore. And thank you very much.
Thank you so much. Are there any questions? I think after this very nice talk, I imagine I have a lot of questions to ask. So please switch on your micro and ask a question if you want.
Can I ask a question?
Sure.
Yes, so you mentioned the case of class 7 surfaces, and there was a conjecture about convergence to some form alpha.
Yes.
So if this conjecture were true, am I right to assume that this alpha will be a closed one form?
No, it's not closed. No, that's not what you get in the case of the Hopf surface. It's not a closed one form.
Okay, it's not. Okay, so that answers my question. And a second question. So when you mentioned some special results about Hopf surfaces, are these true for any Hopf surface or only for the diagonal ones?
So Valentino and I considered these, I think what you're calling the diagonal ones, where you quotient that you have like a alpha times Z1 and beta times Z2, yeah. And you take the alpha and beta to the same absolute value. Yeah, so Valentino and I considered that case. And then Greg Edwards considered the case where the alpha and beta have different moduli.
And there are also the so-called non-diagonal ones that you have a really nilpotent part.
Yeah, I don't think anyone has looked at those.
Yeah, so these don't have a structure of elliptic vibrations. So it's probably interesting case.
Yeah, it could be interesting to look at. Yeah, I don't think anyone has thought about that.
Okay, thank you.
I do have a small question actually. So can you explain the step from the leaf of the distribution to how it provides this global spherical shell? I mean, you mentioned that on your slide. Is it clear even this step if you get this?
Well, no. I mean, I think that the conjecture is that one has to prove that a leaf is a global spherical shell. I mean, I'm not asserting that it's automatically that.
Okay, so there is a lot of work to do.
No, yeah, I mean,
and about this Inoue surface case. So in the Inoue surface, we get T infinity, and do we get the smooth convergence?
Sorry, in which case I missed?
In the Inoue case.
In the Inoue case, smooth convergence is not known. We proved C0 convergence.
You get
in some special case, we got C1 convergence.
But you expect a smooth convergence, or you think that there could be?
We expect it, yes. But unless I'm missing a paper that I don't think that anyone has proved the smooth convergence. I think it's still open.
And also, when you define your T, your capital T, the maximum time, so you explain that you are able to compute it, right? In certain cases.
Yes.
But do you have some information on the psi, which enters in the spatial?
No.
Is something canonical in a certain sense? Psi or?
No, not really. I mean, of course, for each time t, it will be a different psi. I mean,
but for the capital T, it's the maximum one.
For the. Well, yeah, but the thing is, you're taking the soup of all these little t's for which there exists a size. Yeah. You can't take a limit of the size. I mean, the size will not converge to some smooth one as you take t goes to little t goes to capital T. Rather, for each little t, there will exist a psi. But no, I don't think there's anything particularly special about that. I mean, some cases you could be quite explicit, I think.
Okay. Okay. So let's see if there are other people who want to ask a question. You can also write in the comment in the chat box if you have any question, like did Stephen Watson before.
I guess I have a question, not directly connected to one in the chat. So I work in sort of lower brow versions of geometric flows, so motion by mean curvature and higher order variants. So I guess one question I have is that you can take evolutions like motion by the Laplace Beltrami of the mean curvature, and that's fourth order parabolic PDE. And those don't suffer from the types of shrinkage effects that you're describing here. So the asymptotic fate of such solutions, since they're area or volume preserving. So when you have your point 2 and open problems at the end, this finite time collapse, and you suggest perhaps one should look at other flows, are there higher order parabolic flows that might be interesting to consider here?
There certainly are, but they're very hard. I mean, I think I wouldn't look at them in the Hermitian case. I would go back to the Kähler case where things are simpler. And there, the flow that people are interested in is the Calabi flow. And that's probably the most natural fourth order equation on a fourth order parabolic equation on a complex manifold. And very little is known, actually. So
is that because you don't have maximum principles?
Exactly, yeah. Without the maximum principle, people are really stuck. So there's no equivalent of this maximal existence time result, which is known. So I think it's pretty hard. I wouldn't look at it in the Hermitian case because I think it's already hard enough in the Kähler case.
Mm-hmm. Okay, thank you.
Okay. Are there any other comments, remarks, questions? If not, so let's thank the speaker, I mean, virtually, as we can all do by pressing reactions on the bottom line and applauding as it should be for this great talk.
Thank you very much.
And I hope to see all of you next week.